Hello everyone, welcome to our channel Tech Tutor for You. This is Dr. Maheshwari. Today I am going to discuss about the graphical and phasor representation of AM signal. Before reading these representation, you have to get knowledge about the mathematical representation of amplitude modulated wave. The corresponding video is available in our channel. If you want, you can check it out. Coming to the representations, one of the general representation of AM is graphical representation. For generating an amplitude modulated signal, we are in need of an amplitude modulator with respect to the two input signals. One is the low frequency input, that is the message signal. Another one is the high frequency input, that is the carrier signal. For the message input signal, Vm is the peak amplitude of the message input signal, that is positive peak amplitude of the message input signal. And at the another end, the negative peak amplitude of the message input signal is nothing but minus Vm. If it is a low frequency signal, means the corresponding time period should be very high. For the carrier input signal, Vc is the positive peak amplitude of the carrier, minus Vc is the negative peak amplitude of the carrier signal. This is one complete cycle of the carrier signal which has lowest time period, which is nothing but high frequency signal. You have to consider an amplitude modulator. Initially, we are not going to apply any input signal as the message signal. Only carrier should be given as input to the amplitude modulator. If it is so, from the amplitude modulator, the constant carrier signal will be the output. After that, you have to give your input as a message signal by varying its amplitude. Once the amplitude modulator receives the message as the input signal, according to the definition, the carrier voltage is going to be varied. That is, either it is going to be increased or it is going to be decreased, depending upon the maximum value of the message at the positive end as well as at the negative end. The carrier voltage is going to be varied. So, at this point, the very first value, which is nothing but the carrier voltage as per your second input, and the message signal is varying continuously. Therefore, the output of the amplitude modulator is also varying continuously. That variation from the origin, if it is at the maximum value, means that can be represented as Vmax. In the same way, the variation is very less from the origin, it can be represented as Vmin. So, if your input varies, if the input varies, then the output of the amplitude modulator wave is varied. Then the outer layer of the amplitude modulated wave looks like your message. Therefore, it is 2 Vm. So, this region carries the value as 2 Vm. So, this region from the origin carries Vmax. This region from the origin is represented as Vmin. This is the zero amplitude axis. This will be called as the envelope of the amplitude modulated wave, or simply AM envelope. So the AM envelope is nothing but your original message signal, because the carrier voltage is going to be varied with respect to the message voltage or message input signal. So by using this graphical representation, we are going to calculate a modulation index. Modulation index is nothing but the ratio between peak amplitude of the message signal to the peak amplitude of the carrier signal. That is, MA is equal to Vm by Vc. MA is nothing but modulation index for amplitude modulated wave. So for that calculation, we are in need of Vm as well as Vc. So from the diagram, we have to observe what is the value of 2 Vm. So this region is nothing but 2 Vm. which is equated to from the graph is the maximum value, that is Vmax minus Vmin, which is nothing but 2Vm. So 2Vm is equal to Vmax minus Vmin. So from this Vm is equal to Vmax minus Vmin by 2. As well as we have to find out Vc from the graph. From the origin, this region is nothing but Vc. From the origin to this value is nothing but Vc. So this is nothing but the combination or the addition of this region and this region from the origin. So this value is equated to Vmin and this value is equated to, that is from here to here, half of 2Vm. Half of 2Vm is Vm. So Vc is Vm plus Vmin. So from the diagram, Vc is Vm plus Vmin. So we know that Vm is Vmax minus Vmin by 2 from the previous expression. So go for simplification. Take LCM. So we will get Vc is equal to 2 Vmin plus Vmax minus Vmin divided by 2. So finally we will obtain Vc is equal to Vmax. 2 Vmin minus Vmin is Vmin divided by 2. So substitute the value of Vm and Vc in the modulation index. You will get the equation for modulation index with respect to Vmax and Vmin is Vmax minus Vmin divided by Vmax plus Vmin. The third representation as well as the last representation of AM is phasor representation of corresponding output wave. For this, always we have to take the reference phasor as the carrier signal. So we have three components under the amplitude modulated wave, which is nothing but carrier component, USB component and LSB component. The carrier is the reference one, or we can say it as a center wave. So if it is a reference wave with respect to the magnitude is carrier voltage as the magnitude of the carrier signal. So from 0, point some constant voltage as the reference voltage to plot the respective other respective component. And above the carrier we have the component which is called as USB, and below the carrier we have the another component which is nothing but LSB component. And what is USB means omega C plus omega M, and LSB means omega C minus omega M. So above the carrier wave, above the carrier frequency, we have the greater than carrier frequency as USB component and lesser the carrier frequency as LSB component. And the corresponding magnitudes of USB and LSB component is MA Vc by 2. So from Vc, some constant point to be noted above the reference carrier, which is nothing but MAVC by 2. From here to here, it is also MAVC by 2. So we have three components, three voltages. One is VC from here to MAVC by 2, and this one is also MAVC by 2. And the another two phasors to be represented in opposite direction, which is nothing but angular frequency of the message signal. So since the omega C as the reference 1, the rotation of the message signal totally opposite in direction for the USB and LSB component. It is clockwise direction for LSB component and it is anti-clockwise direction for USB component, omega C plus omega M as well as omega C minus omega M. This is the rotation of the message signal. So finally, the combination of carrier component, USB component, LSB component producing the resultant wave is nothing but amplitude modulated wave. Thanks for watching this video.